You perhaps know calcium carbonate better as limestone or as a wallboard or as a powder that once dusted the lapels of professors. But for some creatures, the chemical mixture CaCO3 is used to build home sweet home. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology. And in this episode, shells are beautiful, sometimes collector's items, but their essential function is to offer protection for the animals that wear them. They have different shapes and sizes, and each tells a tale about the environment, both physical and biological. Mammoth ancient oyster shells suggest the sizable impact that humans have had on ecosystems. The disappearance of squid and octopus armor tells us about the evolutionary pressures in prehistoric oceans. And the debate over just when plate tectonics broke up the Earth's early global shell tells us about geological processes that may be taking place elsewhere in the universe as well. It's Shell on Earth.
Even a child can figure out why an animal might have a shell. It provides an environment that's hardened against the whims of its surroundings and the attacks of predators.
But when did nature figure out that this particular design offered a better chance for survival?
Shells have a really deep history. We see that there are organisms arising in something called the Cambrian Explosion, which is a time about 540 million years ago, when we see all sorts of shells appearing in the fossil record.
Thanks to several 100 million years of evolution, there are many critters that are hardened to the world. On land, you've got your armadillos, turtles, and porcupines. Underwater, you might have clams, lobsters, and oysters.
With its wavy grooved surface and the promise of a pearl, or simply dinner, the oyster shell is iconic. Rowan Lockwood has spotted and dug up many abandoned shells, new and ancient, around the Chesapeake Bay, close to her digs as a conservation paleobiologist at the College of William and Mary in Virginia.
So they're made of exactly what other shells are made of. They're all made of a mineral called calcite. They're just made in a slightly different way. I like to think of oysters as being more functional rather than beautiful.
Yeah, but they probably don't care about the aesthetics themselves, right? so I mean, is this a better shell design for protecting against whatever it is that eats oysters, other than bon vivants?
It is. So these are animals that live above the sediment, so they are constantly protecting themselves from stingrays, from fish that eat them, from crabs, etc. So having a nice thick shell, even if it's a bit of an ugly shell, is a good way of protecting oneself.
Well, why those deep nooks, those furrows in the shell?
People have linked that to a particular kind of snail called an oyster drill. And these oyster drills get in. If you don't have very many nooks and crannies, it's easier for the snail to get in there and kind of bore its way into the oyster and eventually eat it for dinner.
Okay, so how big are the shells when these guys start out? I assume they're smaller than they end up being. I mean, and how quickly do they grow?
So in the bay today, when these things are born, they're almost microscopic, a little bit smaller than the size of a sesame seed. And when they reach their full adult size, they're probably about the length of an adult thumb. And then they eventually might reach maybe 100 millimeters, the size of your hand, a little bit over a hand, by the time they die.
Okay, and they're made out of calcite. What is that? I mean, is that like a wall board, calcium carbonate with, carbon dioxide and calcium somehow extracted out of the water there?
Nice job. I got to give you a gold star for that. So calcite is made of CaCO3, so that's calcium, carbon, and oxygen, all laid down together in a framework of calcium carbonate. You can think of it a little bit as kind of a more organized form of chalk. But it's made out of the same stuff that chalk is made out of.
And where do the oysters get this stuff? I mean, do they order it online? Where does it come from?
Oh, absolutely. Next day, delivered by drone. No, there's plenty of calcium carbonate in ocean water, actually. It's very common in ocean water. And so marine organisms, like a lot of oysters, are just pulling it out of the water to be able to build their shells.
Okay. Now, you're not studying the oysters so much that are in the Chesapeake Bay today. You're studying oysters from 80,000 up to, half a million years ago that lived in the Chesapeake Bay. I mean, that's fairly old, although, it's not like the dinosaurs or anything. But how long have oysters been around? I mean, I can't imagine that they just appeared half a million years ago.
Oh, no. These are ye olde oysters, but these oysters and this particular lineage was actually around at the time of the dinosaurs. So oysters in this lineage have been really around for about 80 million years.
But then, in just the last century, the oyster shells in the Chesapeake Bay have been changing. They're much smaller than they once were. Dr. Lockwood discovered this after digging up ancient shells for comparison.
They are big, they are heavy, and they would have served probably a family of 4 if they wanted an oyster dinner.
So she had encountered a scientific mystery. Why were oysters from 80,000 to 500,000 years ago so huge? Today in the Chesapeake Bay, which laps the shores of Virginia, Delaware, and Maryland, oysters are not only smaller, their dwindling numbers have become a special concern.
Dr. Lockwood studies this particular seashell by the seashore in order to establish a baseline ecosystem for the prehistoric Chesapeake Bay, one that might guide an approach to restoration. She wants to know why the tiny Chesapeake Bay oyster shells are shells of their former oyster shell selves.
Restoring the habitats of oysters and their former abundance is good for dinner, but also for the environment, because these guys are natural water filters.
So when I arrived at William & Mary, I was really intrigued by the fact that oysters in the Chesapeake Bay have been suffering for over 100 years, but that we've never really seen a healthy oyster reef. By the time biologists started collecting data, all of the healthy reefs had already been over-harvested. So I really started to wonder whether we could use the fossil record to really get a glimpse into what a healthy oyster reef looks like.
Okay, well, this is a field called conservation paleontology, right? You're not content to compare today's oysters with those of a few hundred years ago. I mean, I'm thinking maybe the oyster population was different when, the settlers from England first arrived in eastern Virginia. You're looking at oyster shells from 10,000 years ago or more. Why is that important, 10,000 years?
Well, it turns out that humans in the Chesapeake Bay Area have been harvesting oysters for almost over 10,000 years. So first the Native Americans, then the colonial settlers. And so if you really want to see what an oyster reef looks like before human disturbance, you need to go even further back. So I'm going back between 80,000 and about 500,000 years ago.
You've been looking at these oysters from long ago. Where do you find them? I mean, I would say in a museum's collection, but obviously that's not where they're found. How do you get hold of oysters that, existed, I don't know, a couple of 100,000 years ago?
So I do a lot of traveling up and down rivers in and around the Chesapeake Bay. I spend a lot of time in boats and kayaks and canoes, and then I spend a lot of time getting in touch with landowners and asking for permission to collect fossils from their land. We have fossil oyster reefs that are located all around the modern Chesapeake Bay and are relatively easy to sample from the shoreline.
So you're essentially just digging them up in the dirt, not from the bay itself.
No, absolutely. They were deposited when sea levels were much higher, and so when sea levels dropped, I can basically boat right on up to them and collect them out of the cliff.
So the most impressive thing about these fossils, and I understand you have thousands of them, which probably beats the guys who study dinosaurs, right? They probably don't have thousands of stegosauri.
I like to think so.
Yeah, well, they probably envy you that at least. But I think, a layperson would probably be impressed by how big some of these oysters are. How big are they?
Well, this was the thing that really caught my eye when I first started working on these oyster reefs. The oysters are huge, so they're about 3 times the size of a modern oyster. And you can find them preserved in these beautiful fossil reefs. The shells are still together in place, and they're still lined up the way they were when they were alive. And so they're sitting there right in the cliff for us to study.
Okay, so they're several times. I mean, how big is that? I mean, is it the size of a dinner plate? How big are these ancient oysters?
Yeah, so they're not as round as a dinner plate, but I think they're definitely as long as a dinner plate. And I like to joke to my students that you could use these things as doorstops.
But, I mean, why were they so much bigger then? Did they have a better diet? Why is it that they were able to bulk up 100,000 years ago, but not today?
That was one of the first questions I asked, is why these oysters are so much bigger. I wondered if maybe they were growing faster. than oysters in the bay today, or maybe they lived longer. And so what my students and I did is we used a tile saw to cut through these shells, and then we collect tiny bits of shell powder. We can use the oxygen isotopes, the oxygen atoms in that shell powder, to help us reconstruct winters and summers. That lets us count the number of years that these oysters were alive, what their lifespan was. And from there, we can basically find that these oysters are big because they lived much longer than oysters do in the Chesapeake Bay today. Some of these oysters lived 15, 20, 25 years before they died.
But today they don't live so long. I mean, what's shortened their lifespan?
Well, almost all oysters in the bay today live for 5 or 6 years before they die, and they either succumb to harvesting, so we have much greater harvesting than these oysters have ever experienced before, or they succumb to disease.
It sounds like what you're saying is that the fact that we go oyster fishing, if you will, if that's the right term, right, is responsible for the fact that the oysters we see are all small.
It's a big one. So if you look at how we harvest oysters, we preferentially choose the big ones. And this is a problem for oysters because the number of offspring that they have is directly related to how big they got. So the bigger ones have more offspring. If you preferentially eat the bigger ones, you're removing them from the population just when they're reproducing the most.
Well, that's really a kind of sea change in our attitudes, is it not? If that term's appropriate, by the way. I mean,
that was terrible.
I mean, when you think of conservation, you think of the policies in which we try to protect the young of a species. You know, don't fish out the fry, so to speak. But maybe that's just a natural consequence of our own tendency to protect the babies. But in fact, it's the old that we should be protecting, right? Not the young ones?
Well, I would argue that for oysters, you get much more bang for your buck if you protect the adults. So you could protect a bunch of larvae, and 1 in 1,000 of those oyster larvae is predicted to survive, or you could protect an older oyster, which is going to produce over 1,000 larvae per year. And so for me, it makes more sense to protect the adult than it does to protect those larvae.
What's the benefit of restoring the oyster population to the Chesapeake Bay? I mean, you know, it sounds nice, and I'm all for the oysters, but if I ask myself, okay, but who cares, what would you answer?
All right, well, the oysters actually have 2 big functions in the bay. So they are the water filtration system for the bay. If it weren't for the oysters, water quality would go way, way down. And it's estimated that in their heyday, the oysters were able to filter all of the water in the Chesapeake Bay in about 3 days. In addition to filtering the water, they're what are called ecosystem engineers. They build these 3D reefs on which other organisms, especially organisms that we like to eat, like blue crab and a variety of fish species, they build the habitat on which these different species live.
That's truly amazing. They filtered the entire Chesapeake Bay essentially in 3 days' time. I mean, that's a lot of, I don't know, sucking in water. I mean,
it's a lot of oysters.
Any idea how many oysters are in the Chesapeake Bay, order of magnitude?
Oh, gosh. I wouldn't like to guess today. I will say, though, that people have estimated how long today it takes for all of the water in the bay to be filtered by oysters, and now it's closer to 300 days. So we've gone from 3 days to 300 days in about 100 years.
Wow.
One of the really interesting things about oysters is that they're hermaphrodites. They start off their lives as male, and then when they reach a certain size, they become female. And so it turns out that if we're preferentially harvesting the big oysters in the bay, we're also preferentially removing females from the population. So it's sort of a double whammy where we're fishing the largest, most reproductively active, but also preferentially female oysters in the population.
All right. Well, finally, Rowan, if this afternoon we put you in charge of conservation for the states of Virginia and Delaware and Maryland, what would be the goal, and do you think you could achieve that goal within a lifetime?
For me, it would be all about sanctuaries. So right now, if you look at the approach that we take to preserving oysters, we really tend to focus on the early life years of the oysters. We put out extra shell for them to settle on. We introduce new larvae into the bay, but we really don't spend a lot of time or energy preserving the adults. So I would strongly recommend a more permanent approach to sanctuaries. Right now, if you look at Virginia or Maryland, we don't have any long-term sanctuaries. We might set aside bay bottom for 1 or 2 years to preserve the oysters, but we don't do it over the long term. And if these oysters are supposed to live for 15, 20, 25 years, our sanctuaries have got to be long-term sanctuaries that are protected from harvesting. If we were to do that, quite honestly, the oysters would start to come back on their own.
Rowan, Lockwood, I guess for somebody who's very fortunate, you could say the world is their oyster. But in your case, I guess the oyster is your world. Thank you very much for speaking with us.
Thank you.
Rowan Lockwood is a paleobiologist at the College of William and Mary in Virginia.
And what an interesting conclusion that, contrary to the conventional wisdom, the best thing to do to spare the oysters is not to spare the child, but to spare the adults.
Well, if shells are such great defense mechanisms, why did squids and octopuses shuck theirs over the course of evolution? Find out what these cephalopods gain by going all squishy all the time. Next.
It's Shell on Earth on Big Picture Science. It works. Well, let's be honest. No one's going to say that about your deodorant, but with Native, you don't have to have any doubts. And Native offers more than just reassurance. It's made with fewer, simpler ingredients. None of that laundry list of strange-sounding compounds you'll find in the chemical handbook. Native has garnered over 7,000 five-star reviews in places like Women's Health, Good Morning America, Nylon, and, well, more. You can get Native in pleasant but not overwhelming scents, such as coconut and vanilla, lavender and rose, cucumber and mint, eucalyptus and mint, or, if you're a purist, totally unscented. And a special deal for BiPi-Sci listeners, 20% off your first purchase if you go to nativedeodorant.com and use promo code BPS, as in Big Picture Science. 20% off. Just mouse over to nativedeodorant.com and use promo code BPS. Native Deodorant. Effective and, to be honest, simply better. We all may retreat into our protective shells from time to time, but evolution has perfected the calcite variety to give critters permanent defense against predators. Otherwise, the soft, squishy body of these animals is simply vulnerable to chomping carnivores. Consider the squid. If you're a tasty cephalopod with succulent suckers, you might want to drag around a protective shell to ward off enemy epicures. And indeed, squid were once encased in shell, and any animals with a taste for calamari would have to devise a way to break that open.
But today, the squid are shellless, as are octopuses and other cephalopods. Once, they all had calcium carbonate protection. The exception, says University of Bristol paleobiologist Al Tanner, is the nautilus and also some squid which have a vestigial shell inside their bodies, but it's small. Otherwise, these animals have all gone soft. So if shells are so effective, why wouldn't all prey animals don them? Well, it turns out there was an evolutionary advantage to ditching the portable housing.
And to get an idea of what these squid shells once looked like, we refer you to the coiled shell of the extinct marine mollusk relative, the Ammonite.
One of the most iconic fossils is the Ammonite, which is the spiral shell ranging in size from a couple of centimeters to over a meter in diameter. And these were the ancestors of cephalopods. So we're trying to understand what are the dynamics of moving from these heavily shelled organisms like the ammonites into the diversity that we see today with the octopuses and cuttlefish.
Were there ever things that look like squid or octopi, I guess it's octopuses, that, had like an ice cream cone shell around them?
Yeah, that's right. So in the past, at the same time as the ammonites, there were things called belemnites, which are slightly less familiar, but they would have looked much like a squid, but with a kind of long cone-shaped shell. If you're in a natural history museum shop, they often have fossils of ammonites and belemnites together because they're so common in the fossil record.
They've lost their shells. That's clear to anyone who's seen them. But what were the evolutionary pressures to do that? Shells offer obvious protection. Why would you throw away your Kevlar vest if you're an octopus?
People have wondered that for a while. And what we see is that the origins of these groups, it coincides with a really major shift in ecologies. Now, it's in the middle of a time called the Mesozoic, the time of the dinosaurs. So this is between about 60 and 200 million years ago. So that's a really long time span. But we can see that the squid, in particular, have a burst of diversity at the same time as fish do. So fish are diversifying at this time because their predators are changing also rapidly in the marine realm. So the ammonites and the belemnites that we mentioned earlier, these animals were slow, they were very heavily armoured. Their tactic for survival was to hide inside their shells. However, we see that predators developed these much stronger jaws, much more strongly made teeth. So clearly there was an advantage to becoming specialists in crushing these shells. And so it started to become a better idea to be fast and agile, and the fish were already doing this. The squid and the octopuses were losing their shells in order to become much swifter, more agile organisms, because that was the only way to survive these novel predators who could get through their shells.
It was better to turn in their tanks and replace them with a jeep. That agility was more important than armor.
Yeah, absolutely. Octopuses have become ambush predators. They are good at hiding amongst the rocks. They're good at camouflage. So is squid, but they have these lifestyles which would be very difficult if you were lugging around an enormous shell. The squid are very fast, and the octopuses want to squeeze into small spaces. So a shell is a really bad idea in either of these cases.
I wonder if they have this penchant for squeezing into small spaces because they remember when they had a shell. Well, what about some of their other abilities there, Al? They can change color in the case of the cuttlefish, squirting ink. Did these evolve before or after they lost their shells? Were these, sort of a new armament in a way that kind of replaced the shell, or were they there all along?
So we know that the ink sacs were definitely there beforehand because we see them in the fossil record. So ink, the type of ink that cephalopods use, preserves really well. In fact, there's even cases of people demonstrating how well it preserves by grinding it up into a powder, adding some water and using it in their pen. It's more difficult to know what their camouflage abilities were, but I would speculate that it wouldn't have been like we see today, because obviously you can't change the colour of your shell, and also we have the shelled nautilus around today, which, as far as I understand, doesn't have much camouflage ability. In terms of tentacles, we know that the suckers and the tentacles, they had been around for a long, long time. They're evolutionary, go back very deep distance, perhaps all the way to 540 million years, when we see the origin of these types of animals.
Well, are there any hard parts in these guys now? I mean, you sometimes see beaks, at least in the movies, but I mean, do they have any bones or cartilage, even teeth?
No, they don't have bones or cartilage. Some of them in the past, as well as suckers, they would have had hooks on their tentacles, which sometimes preserve in the fossil record. Today they have beaks, as you mentioned, but those beaks don't really preserve well, and when they do, they don't tell us a great deal about the organisms.
Finally, Al, cephalopods, which evolved from mollusks, oysters, snails, things like that, they lost their shells, but other mollusks kept theirs. I can imagine oysters would have liked some swimming ability, but they didn't develop it. Looking at the big picture here, would you say that the number of shelled species, at least animals, not talking peanuts, is increasing or decreasing or holding steady? Are shells still relevant today in the way that they used to be?
Yeah, they definitely are. I mean, evolution is about just doing what's necessary to continue surviving and continue reproducing and just passing on your line. So plenty of these strategies are still completely relevant. So for, say, the mussels and oysters, they tend to stick to rocks and remain there, and their strategy is just to close up whenever anything comes close, and that is still a relevant strategy, and in many cases they haven't really changed much for millions of years, and that's just a testament to it being a good strategy. And I guess in contrast to that, what we've seen in this research on cephalopods, we see really rapid change. So some are quite static, some are, a good idea from the start, and so they don't really change over time. Others are much more prone to change, whether it's from your predators or from the environment, or maybe even genetically at its lowest level. And so in different areas, we see really rapid and quite dramatic evolution, like we have with the squids and the octopuses and the cuttlefish.
If it isn't broken, don't fix it. But if it is, change with the times.
Yeah, you've got to change, yeah.
Al Tanner, thank you so very much for speaking with us.
Oh, you're welcome.
Al Tanner is a paleobiologist at the University of Bristol in the UK.
I've seen all those ammonites in the murals that you find at the local Natural History Museum. And they look like sort of, frisbees on their sides.
They're swirling.
Yeah,
right?
they kind of swirl. But, you think about it, a lot of the shells are swirled. And thinking about it from the standpoint of a physicist, if you will, by coiling them up like that, you get a lot more room on the inside for the critter, and you have less surface area for the weight. So it's a better design, and it's probably much tougher too when you have a curled up shell. So I guess it's harder for the predators to get inside.
Certainly there are advantages to it, but can you imagine a squid or an octopus back then stuffed into one of those shells?
Yeah, no. Where were their eyes? They weren't inside the shell, were they? I hope not.
I don't know, but they had advantages to ditching these shells.
Yes, they were. Well,
perhaps they just wanted to ink different.
Yes, that's possible. But it reminds me of medieval times, right? When your best defense in war was to wear a suit of metal, right? And then they invent gunpowder, and you would think, man, all right, let's make the metal thicker. But that's not what they did. Rather than making stronger shells, they got rid of the shells altogether, and the soldiers began running around essentially in street clothes.
So you're making a parallel between cephalopod evolution and the Middle Ages and the Knights of the Round Table?
Well, I don't know if they were all round table. That was a little earlier. But yes. The answer to your question is yes.
Okay, so these guys, they had an enormous advantage by ditching their armor and becoming more nimble. They could be faster.
That's what he said. And that's the proof is in the pudding. In other words, what they were putting on, and it wasn't shells anymore. I can believe that because it was really this funny arms race where the fish developed strong jaws, and these guys, ditched the armor. I mean, that shows you what was important in these ancient oceans, right?
Right, and for the octopus, it was an 8-armed race.
Yeah.
8 arms race?
I get it.
But maybe if the octopus changed, then the squid wanted to do it because it was kind of a squid pro quo situation?
It could be, but
Am I the only one with the cephalopod puns today?
I think it's also interesting that these guys were so clever.
True. Highly intelligent.
Yes.
Octopus are
They're
highly
very,
intelligent.
very ingenious. So it shows you what pays off in evolution. Speed, agility, cleverness, those are all things that work for these cephalopods. And obviously it worked for our ancestors too, none of which had shells, not in the recent ancestors, and they eventually became clever as well. So
now, Dr. Tanner, what he's told us here is that these animals used to have shells, they no longer do, but he didn't explain some of the scientific detective work that went into how they figured that out. And so we have a little bit more from Dr. Tanner, because one of the questions you might have is how he worked out the timing of these physical changes to go from cephalopods being shelled to non-shelled as they are today. And it's a little tricky in this case because while there are some fossils of ancient squid with their ink sacs preserved, as well as octopuses, there really aren't many samples of these soft-bodied animals. But fortunately, scientists have another method to map out the evolutionary changes, and it's called a molecular clock.
Molecular, when we say molecular, we mean using DNA, but also RNA and also protein sequences from living organisms.
And this genetic code can be used to work out the timing of evolutionary changes because the molecular clock relies on a more or less steady mutation rate of DNA.
You know, the way I look at this is the way I look at the mutation of automobiles. I mean, imagine somebody gives you 1,000 cars, from the Model T all the way up to, I don't know, a Tesla or something of today. And you don't know much about cars. You never studied cars. You never owned a car. But your job is to sort of order them sequentially in time. And you could do that because from year to year, the cars don't change that much. So you would just see, here's the evolution toward chrome bumpers or whatever it is. And that would allow you to, kind of order the procession of cars down the years. You could get the Model T at the head of the line, the Tesla at the end of the line. It's something similar with these DNA mutations. It's accumulated changes.
Well, I've never heard of them as automobile mutations, but okay, we'll go with that analogy. At any rate, in evolutionary biology, these mutations are passed down, but in the case of the mutations they look for when they're looking at this molecular clock, those mutations aren't significant enough to change the organism.
It would be like spelling mistakes in a book. A spelling mistake might change what a word looks like, but it won't change the meaning of an entire sentence, or at least it would very rarely do that. And therefore these are passed down through time because they don't need to be corrected, because they don't really make much difference to the organism.
But these benign mutations are a great help to scientists because they can use them to track the changes with time. So, for example, if fossil A has mutation X and Y and fossil B has mutation X, Y, and Z, then you know that fossil A predated fossil B, and then you know what order to put them in.
Yeah, right. And you don't need the critter itself if you're talking about related critters that might not fossilized well. You can use the fossils of the species that you do have.
Cephalopods are related to the other mollusks, so that's like the land snails and the sea snails and oysters and mussels. And they've got a good fossil record, so we can what we call calibrate the timing against those fossils. And then for the areas where we don't have a fossil record, so in this case the octopuses and squid and cuttlefish, we can then interpret from the genetics, guided by a known fossil, when they originated. And so that's the exciting thing of the work we've done recently, is that we've figured out when all of these different 8 and 10-armed organisms, the octopuses and the squid, arose and had a major shift their ecology.
So when you give those guys material to study, I guess you have to give them shell. Okay, we're taking the shell game a step farther. We've talked critters, but could it be that the Earth itself was once encased in a giant globe-spanning shell? The latest ideas in an ongoing debate over plate tectonics.
It's Shell on Earth on Big Picture Science.
Shells are some of the oldest and surely among the most straightforward defense mechanisms on Earth. Squids and octopuses may have found reason to shuck these hardened houses, but other animals, such as oysters, have kept them. However, the oldest shell may predate the casing of the Ammonite, that 240 million year old ancestor of the squid, and even the first shelled creatures identified with the Cambrian Explosion 540 million years ago.
The oldest shell that Earth has produced may have encased not an animal, but the Earth itself, back in the days of the Archean Eon, 4 billion to 2.5 billion years ago, a time before there was life on Earth.
When was the Earth's crust a big plate or shell? Well, that's an ongoing debate amongst geologists. Today, the Earth's crust is broken up into 10 large and 6 small pieces that continually reshape our planet by diving under each other in subduction, and, by the way, producing earthquakes and volcanoes as a result, or by spreading apart and forming new ocean basins.
But when did all this moving and shaking begin? Well, first let's set the scene, says University of Maryland geologist Mike Brown, who takes us way, way back.
We have to go all the way back to the beginning of the solar system as the solar system formed. We can imagine that as the Earth formed, it was being formed by planetesimals, that's small planet-like pieces of rock, like meteorites, that bump into each other and aggregate together, eventually to form a planet. During this process, there was a planet about the size of Mars that collided with the proto-Earth. And this produced an enormous amount of energy that left the Earth molten, essentially, from surface right down to the iron-rich core. And as that molten Earth developed a crust at the surface, the question that we try to answer is, how long did it take for plate tectonics to form?
Now, some people argue that plate tectonics formed early on in Earth's history, soon after the formation of that outer shell, roughly 4.6 billion years ago. Others would argue that because the interior of the Earth was hotter than we thought, the Earth behaved differently, and plate tectonics came later, a relatively recent development at 3 billion years ago.
Dr. Brown and his team have argued in a paper published in the journal Nature that plate tectonics started later, that Earth's crust stayed more or less a continuous shell for more than 1 billion years. Okay, Mike, I'm casting my mind back to those early days of Earth, and I'm reminded of those artist impressions that showed a seething, sticky, hot surface of fiery rock, with a few asteroids streaking across the sky in the background for dramatic effect. But it looked like the surface of the Earth was just hot magma everywhere. So is that how I should picture the Earth of some 3.8 billion years ago or so?
No, you should not picture it like that. That is certainly the picture that we used to have 20, 30 years ago, and indeed, pictures like that have been on the front of several popular magazines in that time frame 20, 30 years ago. And that indeed is where the name for this geological period, the Hadean, hellish-like, comes from. But in fact, we now know that there was surface water. There was water at the surface of the Earth. We know that the oldest volcanic rocks that we see have pillow-like shapes and were emplaced underwater. That is how you get pillow lavas that look like piles of cushions, if you will. We know that the surface of the Earth was no more than 100 degrees Celsius warmer than the present day. The question is, how does that interior change in temperature as we go down towards the core? And in the early part of Earth history, it was quite a bit hotter closer to the surface.
Do I get this right that 3 billion years ago, which, after all, is a lot less than the time back to the formation of the Earth, 3 billion years ago, the Earth was completely encased in this shell, this hard shell?
Well, that's a difficult question to answer. I mean, the Earth is completely encased in a hard shell at present. It's just that that shell is broken into about 16 pieces, 10 large pieces and 6 smaller pieces that move relative to each other. We imagine that when this crust first formed, it might have been a complete single plate. It would not necessarily have had a uniform thickness. There would still have been convection inside the Earth, so there would have been areas of the interior which were rising, and as a consequence, there would be areas that were descending, so we would have had a convection system operating in the mantle. And the question is, how long did that last as a single plate? How long did it take until we get to a present-day-like configuration where the entire surface of the Earth is broken into a series of plates that can move apart from each other, towards each other, and laterally sideways past each other?
Okay, I'm still trying to picture this. If I had a time machine and I could go back to 3 billion years ago, what would I see? I mean, was there any visible water? Was there any atmosphere?
Yes, you would see. If we go back to, let's say, 4 billion years ago, a little bit earlier, you would have seen probably that the entire surface of the Earth was covered with water. You would have seen sticking up through that water volcanic edifices, rather like Hawaii sticks out of the Pacific. These would have been distributed across the globe. They would have been randomly distributed, but there wouldn't have been the situation we have today, where we have 1/3 of the globe which is above sea level and 2/3 of the surface which is below sea level. So at present we have what we call the continents, which is the area that's above sea level, and they're made of lighter rock than the oceans, which are below sea level, which are made of heavier rock. In the early Earth, we would have had rock very similar to that under the ocean basins. It might have been even heavier still, and that would have covered the whole surface of the Earth. So the process that we have to go through is recycling that early crust in order to fractionate it, to distill it, if you will, to generate a lighter rock, which we do by melting it to a small degree, which gives us a much lighter material, and create the continental crust.
I see. So, I mean, this sounds like what happens, I guess, in a steel mill or something, where they separate the lighter stuff from the, the slag from the iron.
Exactly.
Okay, so heat does the job here and produces, in fact, the continental crust. But the continental crust depends on the fact that these pieces they're doing their own thing. They're separate pieces, right? How did that get started? I mean, I'm kind of picturing a hard-boiled egg that you wrap with a spoon and you introduce cracks, and then in this case, maybe they start moving around. What produced that?
Well, of course, we didn't whack the Earth with a spoon. So this is the difficult question to answer. I can give you two possible scenarios by which we might be able to explain the development of a global system of plates that can move relative to each other. You have to imagine that the Earth, when it was hotter, would have had material coming up from deep inside. These would be like large tube-like bodies of upwelling mantle material, the material that forms the interior of the Earth. And as these volumes of material move towards the surface, they would have begun to melt because we're going to higher temperatures at lower pressures. So they would generate magma, melt, which comes out as lava, which is what we see at volcanoes like that in Hawaii. Okay? These are quite large. They would produce large areas of magma. These plumes, they're called, these tubes of upwelling material, could have produced enough magma to push down this outer shell and start the process that we call subduction, by which one piece of this outer shell gets pushed under another, as we see, for example, off the coast of Chile in South America, or off the coast of Japan. And these are the areas where we have the biggest earthquakes on Earth at the present day, because we're pushing the surface of the Earth back into the interior of the Earth. The alternative view is that maybe this outer shell, as it moves around, it begins to wear weaknesses, rather like bending a piece of metal. It begins to wear weaknesses in linear zones that then start to break. And we find that some of those can be moved apart by allowing magma to come between them, which means that other pieces have to move together to keep the surface area of the Earth constant.
There seems to be a real controversy developing here, Mike, about when did plate tectonics start. I think, generally speaking, many people thought that it began relatively soon after the Earth was formed, but what you're describing to me here suggests, well, maybe not. How is this controversy going? I mean,
I think the weight of evidence at present that probably we had some kind of regime before 3 billion years that wasn't a globally linked network of plate boundaries. Earlier than 3 billion years ago, we could have had an entirely single plate planet, or we could have had a mixture where in some parts of the planet we had the ability to push material back in a manner very similar to the present day. But it probably wasn't globally linked. Since 3 billion years ago, we've probably had globally linked plate tectonics throughout the remainder of Earth history to the present day. Now, the balance of opinion on that is probably maybe 60%, maybe two-thirds in favor of plate tectonics starting around 3 billion years ago. There is, of course, still a substantial opinion that believes that plate tectonics started much earlier in Earth's history. And this is something which is important in science. It's important to understand. Science works by consensus. So it's not a question of which of us is right. We have differing opinions, and we try and find evidence to support one view or another, or perhaps an alternative, and we try and work towards a common understanding whereby we start to agree that, yes, this is the way it works. And of course, if we always agreed, there would be no fun.
Suppose it's true that the Earth had this skin, this fairly, solid skin, this shell around it, and that plate tectonics didn't start up until, a quarter of the way through the history of the Earth, whatever it is. Why would that matter? How does that affect our understanding of the Earth? Or for that matter, how does that affect the development of life on Earth?
They may not be related. The development of life on Earth almost certainly goes back to probably something like 3.8 or 4 billion years ago, although, as I'm sure you know, the evidence is extremely difficult to demonstrate that life occurred then, and there's a lot of ambiguity, so there's a lot of controversy. The importance of plate tectonics is, first of all, many of Earth's resources are related to plate boundaries. So, for example, we can think of copper production in Chile. This is related to the fact the Nazca Plate, as it's called, is being pushed under Chile, generates volcanism, and those volcanoes concentrate the element copper. And we can think of a variety of economically important deposits that are related to plate boundaries. And so understanding how the Earth works enables us to make better predictions of where we might find economically viable deposits of important minerals and important elements that our society demands, and in particular rare metals for use in things like cell phones, for example. So there's an economic advantage to understanding how the Earth works. It's also just intrinsically important, I think, to understand how our planet developed and how our solar system developed and how other systems similar to our solar system might have developed. And as you know, there's a great interest at the moment in what are called exoplanets, potentially planets that could be habitable in other systems.
It sounds as if the mechanisms that you've described, in which the Earth develops this crust and then eventually breaks up and you get plate tectonics and so forth, which, as you note, are important if you're going to be a technological society, that might be a general phenomenon. I don't know whether there's anything in this story that suggests that Earth is particularly special, except for that big impact that created the moon. I mean, is what happened on Earth something that we should expect to be frequently the case, or is it something relatively rare?
That's a difficult question to answer. I think given the potential number of stars out there, and therefore the potential number of solar systems, on a statistical basis, we could expect to find other habitable planets. In terms of our own solar system, the thing that's unique about the Earth is the fact that we have water. And the reason we have water is because it was probably mostly brought at a late stage of construction of Earth by impacting meteorites. They brought the water to Earth. So there is something unique about Earth within the solar system, and it relates to water. And in fact, the reason that we have the continents is because we have the ability to fractionate these materials that are derived from inside the Earth to generate this lighter rock, and that involves water because we require a source material to melt that has some water in it. So without water, we wouldn't have continents. Without continents and oceans, we might or might not have life. We might not have had sustainable life. So water is extremely important to Earth within the solar system.
Mike Brown, thank you so very much for speaking with us.
Well, Seth, I enjoyed it. Thank you very much indeed.
Mike Brown is a geologist at the University of Maryland in College Park, Maryland.
Indeed he is. And, something interesting he said there that struck me was that the ancient Earth, back in the Hadean times, it wasn't all that hot on the surface. He said it was only 100 degrees centigrade warmer than it is maybe today, And so all those artists' impressions of this churning liquid hot rock, they're all wrong. It wasn't that hot. It was only like the boiling point of water. I mean, I guess that's hot.
But the big question is when that heat began to break up the shell that covered the Earth and plate tectonics began.
Yep. It's like, in astronomy in a way, that some of the biggest questions in biology and geology and, of course, paleontology are about dating things. And we've heard about a couple of different ways to date things. I mean, if you're talking about rock, really old rock, like the Pilbara Hills in northwestern Australia, and I've actually been there, the oldest fossils that we've ever found are there. How do they know how old the rock is? They do that with radioactive decay. That's a well-known laboratory procedure that can give you fairly accurate dates. I mean, within a few percent of how old a piece of rock is.
And that's relevant to Mike Brown, Professor Brown's story about trying to understand these ancient processes from billions of years ago. So you can use that kind of dating for rocks that are billions of years old?
Well, true, yes, because he was finding, evidence in the morphology of the rocks, how they're shaped, but also in fossils and so forth and so on. But, if you want to know how old something is, if it's that old, billions of years, then you use radioactive dating mostly.
Now, if you have something that's in the more recent deep time.
It's not so deep. Shallow time.
Well, it might be deep ocean in this case. In the case of the understanding the evolution of the squid and the octopuses and how they lost their shells, you can't use fossils, you can't use rocks because these are animals, but you can use this technique called a molecular clock.
Yeah, that's right. That there's, this constant mutation going on in our genome, and to begin with, because if you just look at the mutations, you can tell which fossil preceded another's fossil, if you've got fossils. But also, you have some idea of the rate of mutation. So in a way, there's kind of a ticking clock, It's your biological clock ticking, but this is one from, millions, hundreds of millions, even billions of years.
And then in something in the more recent past is understanding how long these oysters lived 80,000 to 500,000 years ago. Dr. Lockwood's study of those oysters in Chesapeake Bay. And in that case, she would cut into the shells and count the rings.
Yeah, that's right. It's just sort of like I think they do some dating of ancient hominids by counting the layers on their teeth or something like that. I'm not so sure about that. But if you found, fossilized tree logs or something like that, obviously you could count the rings. So if you're talking about oysters where the number of rings isn't all that great, I mean, you're talking about 20, 30, 50 rings, then indeed you can gauge their lifetimes. I will say this, that if you're someone who's interested in the history of life on Earth, you got to be grateful for shells, teeth, and anything else that is hard, because those are the things that you get to look at, a couple of 100 million years later.
Thanks to the people who are truly excellent in helping us produce a show each week. Senior producer Gary Niederhoff, operations manager Barbara Vance, and intern Sarah McQuaid.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life, including the nature and threat of nearby asteroids. And a big thanks also to our listeners.
Your ears have been attuned to the Big Picture Science episode Shell on Earth. If you'd like to hear more episodes, you'll find them in our archive at bigpicturescience.org.
And if you're a podcast listener but prefer listening to over-the-air radio because you just don't have an alternative, well, check out the listing on our website of radio stations that carry the program. And if your local station is not on that list, consider letting them know you like the show.
And if you listen to our show via iTunes, we invite you to leave a review on our iTunes page.
And to reach us directly with your comments, throw in some faint praise and then email it all to bigpicturescience@seti.org.